Let's get started with section 10.3, changes in temperature and phase. So here's maybe a familiar situation. You are walking to the beach, you get to the sand, and ouch, the sand is really, really hot on your feet. And so you lay down your towel, you take off your shoes, and you take off running across this burning sand to get into some ice cold water. Well, the thing that we're going to talk about today, specific heat, illustrates why you have these two extremes right next to each other. Why is the sand so hot? Why is the water so cold when they're both exposed to the same amount of thermal energy ultimately from the sun? Well, the reason for that is that they have different specific heat capacities. And so this is going to be defined as specific heat, the energy required to raise 1 gram or kilogram of a substance 1 degrees Celsius. And so if we look over here at this specific heats of common materials, we have, we'll take a look at this set of units first. Joules divided by grams, degrees Celsius. So this helps us remember the definition of specific heat. Energy required. Energy is measured in joules to raise 1 gram of substance, right? That's in grams here, 1 degrees Celsius. Okay, so this is going to help us understand why some substances are going to heat up faster. Their temperature is going to increase faster with the same amount of heat applied, and granted it's the same mass, right? And so we're going to look at an example here. We're going to compare iron and liquid water. So liquid water, this 4.18 joules per gram degrees Celsius, is going to be something that we come back to over and over and over. The specific heat of water in grams is going to be an important constant that you'll use in your problems. So we can see that this is almost a 10-fold difference between iron and liquid water. So that means it's going to take 10 times as much energy in joules to raise water to the same temperature or undergo the same temperature change as the same amount of iron. Okay, so the specific heat of water is going to require 10 times more energy to make the same temperature change than it would be with the same amount of iron. So let's flip back. So in our example, we're going to take iron, we're going to take water, we're going to assume that this is the same mass, and we're going to monitor the temperature of the two of those. We're going to link these heaters underneath, and we're going to observe the temperature change between the two of them. So again, we're assuming that this is the same mass. We're going to assume that this is the same amount of energy. And we can observe very easily that our iron temperature is going up much faster than our water temperature. So in other words, with the lower specific heat of iron, iron will increase its temperature faster with the same amount of energy versus the very high specific heat of water. And so we can see our specific heat capacity equation here, again, goes right along with our units. Q is the amount of energy transferred in joules divided by the mass in grams or kilograms, depending on which unit you're using, divided by the change in temperature. So this C sub P is assuming that the pressure is going to remain constant. We didn't talk about gases or ideal gases, but temperature and pressure are related to each other. So we're going to do this in what we call an open system, where the pressure is constant. So in order to calculate specific heats for objects, we use this apparatus and this procedure known as calorimetry, an experimental procedure to measure the energy transferred from by heat from one substance to another. So again, remember we talked about heat and defined it as the energy transferred from one object to another due to a change in temperature. And we know that temperature, of course, is related to kinetic energy. So this is a basic setup of a calorimeter. It has a reservoir full of water. We have a known mass of water that's important for our specific heat calculation. We know that liquid water has a specific heat of 4.18 joules per gram degrees Celsius. This is normally going to have a lid on this. We would take an initial temperature of the water, and then we would take a final temperature of the water to determine the change in temperature of that water. And again, we're going to assume that all of the energy from that substance, the hot substance, is going to flow directly into our water. We're going to know the mass of that object, and from those data, we would be able to calculate the specific heat. So I just wanted to show you guys quickly a very, very simple calorimeter. So we used these in chemistry last year. This would be to measure the heat of solution. You would put some sort of ionic substance, some sort of substance that would dissolve in water. In here, you have a little stir rod here. You obviously have a lid. And the key part to a very simple calorimeter is when you take it apart. So this is just some foam core. Again, we talked about how well styrofoam insulates. It's going to keep the vast majority of the heat in the container so that it can be absorbed by the water. And you can get an accurate temperature reading. So you put the lid on. There's a little hole here that you would put your thermometer into. And again, the thermometer just needs to reach down into the solution. You take an initial temperature, and then you take a final temperature to get your delta T. So determining specific heat capacity, we did an example problem together during our Zoom session. But just a reminder of what we have to assume, the energy absorbed by the substance is going to be equal to the energy absorbed by the water. This is how we can observe this temperature change from the water alone due to the energy released from that object. Water is always used because we know the specific heat, and it's obviously readily available to us. We can ignore the amount of energy that would be absorbed into the calorimeter itself. So this is a styrofoam cup calorimeter. There are other very basic calorimeters that are going to have the same layout. So the styrofoam cup is going to provide insulation. And we know if we're drinking a hot beverage out of a styrofoam cup, we know that we literally cannot feel that temperature through that styrofoam cup because it's a really good insulator. That's what makes a good calorimeter. So here is our specific heat equation. So again, when we think about specific heat, Q divided by M delta T, we rearrange this equation to solve for Q, and then we set the two Q's together. So C, P, W, water, mass of the water, temperature change of the water, equals the change the specific heat of your unknown substance. You'll most likely be solving for that. Mass of your substance divided by the temperature change of your substance. And of course, you're going to have the initial temp of the water, initial temp of the object, and then a final temp for them both after they have reached thermal equilibrium. So we're going to move on to the next part of our section, latent heat and heating curves. So this is our example heating curve. There's also one in your book, figure 10-13. I apologize, this should not be Fahrenheit, it should be Celsius, but it'll be fine. So we're looking at a heating curve for water. And so we have down at the below freezing, right, 32 or 0 degrees Celsius is going to be a solid, water is going to be solid in the form of ice. We see that the ice is going to increase in temperature as heat is added. That's what we would expect. However, when we're going through a phase change, when we're going from a solid to a liquid, we're going to undergo a phase change called melting. And so when we go through this solid to liquid phase, we're going to see that the heat that is added is not going to increase its temperature. So that's a little weird. Once all of our solid has melted, water is going to increase in temperature with added heat or energy. And then we're going to see another plateau where boiling is going to take place. And we're going to move from a liquid to a gaseous state. Okay, and again, even though heat or energy is added, our temperature remains the same until it is all completely converted. So why is that? That is a very strange sort of pattern. And so when we think about these phase changes, we have to define and expand what heat is. So heat is exchanged between two bodies of different temperatures until thermal equilibrium is exchanged, or between two bodies of the same temperature and there is a phase change. So again, heat is added here, but with no temperature change, we are instead going through that phase change. And so this all has to do with how these particles, these molecules, are interacting in each stage. So when we go through and get to a microscopic version or understanding of these phase changes, we have to understand what's happening with the interaction between these molecules. So at the melting point, the latent heat of fusion does not act to increase the average kinetic energy and the temperature of the molecules in a solid, but instead are used to overcome the potential energy associated with the forces between the molecules. So think of the forces between the molecules like an ionic bond. So between sodium and chloride ions, there is an attractive force. So you have to add a ton of heat in order for ionic bonds to break apart. That's why there's such a high melting point for most ionic substances. That is, the work must be done against these attractive forces to break the molecules loose of their relatively fixed position in a solid. Remember, solids are highly ordered. You can see that in the bottom right-hand figure there. So they can freely roll over one another in the liquid phase. Similarly, energy is required for the molecules held close together in the liquid phase to escape into the gaseous phase. This process is more violent reorganization of the molecules than is melting. The average distance between the molecules is greatly increased in a gas, and hence the heat of vaporization is generally much greater than the heat of fusion for a given substance. So what are these two things, this latent heat and this heat of vaporization? So we know that as we increase in temperature or increase in energy, we increase in temperature. So we're going to see in this table here that we have a specific heat for these three phases. So liquid water, solid water, and water as a vapor. But when we're undergoing these phase changes, we're going to have these other values, the latent heat of fusion of water and the latent heat of vaporization for water. And we can see that this is a much larger value for this particular phase change. We're going to have to add a lot more heat in order to go from liquid to a gas. Then we would have to go from a solid to a liquid. And it all has to do with breaking apart the attractive forces that are going to make solids solids and that are going to make liquids liquids. Now, we're not going to get into those attractive forces. Maybe you remember some of those from chemistry last year, but these are the 5 values we are going to need to do for our example problem when we calculate the Q's, or the amount of energy for A through E in table 10-5.
All right, so let's get back to doing a couple of problems when there is a phase change involved. So we have values. This is from the PowerPoint that is earlier in the video. We have the specific heat at a constant pressure for liquid water, solid ice, and water vapor or gas. So we have these values. Remember our unit here, joules per gram degrees C. This grams could also be kilograms. Down here, we have other values. So the latent heat of fusion, the latent heat of vaporization. This is when we're undergoing our phase change. So remember, from our heating curve of water, we should have noticed that when we're undergoing a phase change, there is no temperature change. Remember, the phase change is to allow molecular reorganization of those molecules from a solid to a liquid in order to break down that lattice, those highly ordered atoms, into something more fluid and something that is going to flow like a liquid. And then in order to go from a liquid to a gas, we have to add even more energy in order to break the attractive bonds between those water molecules, those hydrogen bonds, and release them as gas into the air. Okay, so remember, there's no degrees Celsius here. These are going to be the plateaus, right? So we have the initial from solid to liquid, liquid going through the phase change. We have another initial increase of the liquid temperature. We have a phase change, and then we have the increase of our gas, right? So this is our solid, this is our liquid, this is our gas, and these are our plateaus for that phase change. So what we're going to do, turn to page 376 in your textbook. There's a table 10-5 at the bottom. The third column here, amount of energy transferred by heat, and they're going to be labeled A, B, C, D, and E. So you already have the value there, and we're going to just figure out, do the calculations that accompany that value. All right, so let's start with letter A. It says in here that there are 10 grams of ice. Okay, so this is going to be the M for all of these. So we're not going to reiterate. I'm not going to write it out as something we know. We're just going to plug it in after a while. But this is 10 grams of ice. It's starting the temperature initial equals negative 25 degrees Celsius. And we know that the temperature, final is going to be 0 degrees Celsius, which allows our delta T to be, of course, 25 degrees Celsius. So we have a C, our specific heat, a constant pressure of ice, 2.11 joules per gram degrees C. Our equation, Q equals Cp times our mass, our change in temperature. Okay, so if we plug all of that in, 2.11 joules grams degrees C, 10 grams of ice, 25 degrees C. That's going to equal 527 joules. And in your book, for letter A, it says 222 joules. So we'll call that good enough. Let's move on to letter B. So B is going through our phase change. We have ice plus water phase change. So this is going to look similar, but a little bit different. Q is going to be equal to the mass of our ice plus water times our L of fusion. Okay, so that's going to be the latent heat of fusion. That value is, so we have 10 grams times 333 joules per gram. Okay, and that equals 3,330 joules. In your book, it says 3.33 times 10 to the third, and we would agree that if we remember our scientific notation, that is the same value. Okay, how about for letter C? So C is going to be increasing the temperature, warming up that water. So we have a temperature initial equals 0 degrees C. Temperature final, we're getting, not delta T. Temperature final is going to equal 100 degrees C, because that's our boiling point. And so we have a delta T of 100 degrees C. Okay, our mass, again, is going to be 10 grams. And now we're going to use our specific heat of liquid water. Again, you're going to be using this a lot, 4.18 joules grams degrees C. Plug that all in. Again, Q Cp times m delta T equals 4.18 joules grams degrees C, 100 degrees C, 10 grams. And if you plug that into your calculator, you should agree that that is equal to 4,180 joules. And again, that's letter C in your book. All right, so let's go to letter D. D is going from liquid to our gas. Okay, so again, this is going to be a phase change. This is going to necessitate we use the latent heat of vaporization, which is equal to 2,260 joules per gram. Q is equal to 60 joules per gram, 10 grams. And if you look in your book, you should agree, it says in your book, 2.26 times 10 to the fourth. 2.26 times 10 to the fourth joules. And if you did that math, put into scientific notation, you should agree with that also. And then finally, for letter E, this is where we're going to heat our gaseous or water vapor, water gas, to 125 degrees C. So we have a temperature initial, 100 degrees C, temperature final, 125 degrees C, change in temperature, 25 degrees C. Again, we plug it in. Q equals 10 grams. Our specific heat of water vapor, water is 2.0 joules grams degrees C times 25 degrees C. And if you guys plug all of that in, you should get 500 joules. And your book says 502 joules. So we'll call that good. Now, oftentimes these values are going to need to be added up in order to find the total amount of energy. So if we wanted to add those up to find the total amount of energy, Q, to melt 10 grams of ice at negative 25 degrees C to a gas at 125 degrees C, we would have to add them all up. So it would be 527 joules plus 3,330 joules, 4,180 joules, 22,600 joules, 500 joules, and we would see that that all equals 31,137 joules. Okay, so you may have to do this at the end of your problem, and that's what we're going to do next. We're going to go through an example problem. This is section 10D, number 3 on page 381. Okay, so this question is asking how much energy is needed to melt 200, so here's our mass, 0.225 kilograms of lead. Now we're not using water, but thankfully you have two tables. So we're going to look on tables 10-6, and you're going to look on table 10-4 in order to figure out this problem using lead. Okay, so we have a mass of 0.225 kilograms. If we look on these tables, we have a T initial, 27.3 degrees C. And we would also find out that the melting point of lead equals 327.3 degrees C. So the question's asking us, how much energy is needed to melt a 0.225 kilogram of lead so that it can be made into a lead sinker for fishing? The sample has an initial temperature of 27.3 degrees C and is poured in the mold immediately after it has melted. So we have to go from a solid, we have to raise the temperature of that solid, then we have to go to a phase change all the way to our liquid state. So we're going to end up adding this section and this section together. In order to start this problem, remember, we're going to have Q equals Cp times M delta T. And so we're going to go through our first section here, going from our solid to our melting point. Okay, and so our delta T here is going to equal 300 degrees C. So we're given that the melting point is 327.3. We're starting at our initial temperature at 27.3, and so we have a difference of 300 degrees C. Next, we need to look on our tables to find out our specific heat of lead. So our Cp of lead equals 1.28 times 10 to the 2 joules kilogram degrees C. So let's plug that in. Q equals 2.225 kilograms, 300 degrees C, 1.28 times 10 to the 2 joules kilograms degrees C. And if you add that and put that all into your calculator, it's 8,640 joules. Now we're not only raising the temperature, but we also have to go through our phase change. So now we have to go through and find out the latent heat of fusion for lead, which happens to be, again, you have to look at your tables, 2.45 times 10 to the 4th joules per kilogram. Okay, so let's plug that in. Sorry, I keep forgetting to move this thing up. I apologize. So latent heat of fusion, 2.45 times 10 to the 4th. We're going through our phase change, which means that we're not going to have a temperature change. Q equals mass times L of fusion equals 225 kilograms, 2.45 times 10 to the 4th joules per kilogram equals 5,512.5 joules. And so the question is asking, what is the total amount of energy? So we have to add our 5,000 to go through the phase change. We have to add up our 8,000 in order to go through our heating up our lead to the melting point. So if we add those two together, we get our answer in the back of the book, 14,150